sure it actually is running. Yep.
All right, so let's talk about assessments here. All right, so the next quiz is chapters 8 through 10. Because we meet only once a week, I'd like to have the quiz next week. However, the alternative is to push it off another week, in which case it's due right before Thanksgiving break. And so we do have class then, but sometimes we don't have the full complement that close to Thanksgiving. I would still like to do it next week, but if someone wants to make an argument for pushing off another week, there'll be more material we're gonna cover in the interim that is not related to that quiz, but. Any objections to next week? Okay. So quiz on 8 through 10. All right. Chapters 11 through 14, I typically cover very quickly. I do the quiz a little bit differently for that. For the quiz, I will, at some point, hopefully this week, I will post the homework assignment for this class. And what I mean by that is you will each have your own individual problems to work. I try to set it up so you have the same number of, it depends on which version I pull up, but I try to make sure everyone has the same number within one, same number of plug and chugs within one, the same number of evens, same number of odds. Total number of problems is the same for everybody, but I try to balance it out so everybody has the same level of difficulty for each type thing. That is the homework, that is the quiz that you will do on your own. I mean, you can get help, but that is something that you will do outside of class, and that is something that will be handed in. But, yeah, so that's basically what happens through chapters 11 through 14. Then we get to the material that will be on the last test.
So, when are we doing this at-home quiz?
I need to post it first for what your individual assignments are.
But like, when is the due date gonna be?
I'll pin it down now. November 30th.
Oh, I need to talk to you about November 30th.
I assume that I just reminded you of something as opposed to there's a
Yeah.
correlation there.
Yeah.
No idea what I just did with that marker, so. Oh. Not a good place to do that. Quiz 11 through 14 due. If you went on there now, you probably would find the assignments from a previous class. But what it is, you bring it up, it's a PDF, you bring it up, you'll find your name and then the list of the problems.
Is it under coursework or?
It'd be under coursework and then whatever, I think I have 11 through 14 put together.
What's our last day of class?
It's December 9th,
That's the last day of the semester, our last day of class is the 7th.
the 7th.
But if you, anybody who owes me anything, that you have till the 9th, or through the 9th. I think grades are due the following Monday. Yeah, grades used to be due noon the day after the last day of class, and that was just, that was really fast.
So you haven't uploaded the homework yet?
I have not for 11 through 14 yet. All right, so other questions right now?
So we're gonna have our last test, will that be on the seventh?
Yes.
That'll be on what chapters? Just
15 through however far we get. If you'd like to start it earlier, you know, say 6 through however far we get.
No?
Okay. Just wanted, you have freedom of choice here, we could do
We do
more.
like 50 through 16?
We probably get farther than 16.
Okay.
50. Step over to about 50. Just the 50.
All right, here we go. What can you tell me about an atom?
They're small.
Okay. Any idea how big? Ish, ballpark? All right, small will work for now. What else can you tell me about an atom?
They make matter.
Okay.
One make not.
Yeah, my hesitation is there are other things besides atoms that also create matter, so, A, not B, but A component. Wow. I'll just say visible matter. The atom itself is also comprised of matter. What else? What's in an atom?
Proton, electrons, neutrons.
There we go, all right. So we got these three major components here. We got protons, which can be abbreviated, of course, as a P with a little plus sign right there. The electrons, which can be symbolized by an E with a negative sign there. Neutrons, which is an N with a 0. So why do I have a plus minus 0 there?
The charges.
Okay, so proton is a positive charge. Now the symbol for charge is Q. And so the charge of a proton, anyone happen to know? (1.6 times 10 to the negative 19 coulombs). Unit of charge. I guess the unit doesn't have to be capitalized. Anyone want to take a wild stab at who it's named after?
His name is David. Cool on it.
Yeah, I was trying to think what his first name actually was. We'll go with David for now.
It's gotta be David.
Charles Auguste Coulomb. You know, to be boring, a lot of names together on that one. All right, so that's the charge of a proton. The electron, what's the charge of an electron?
Are we supposed to know this?
Well, I was hoping that somebody's had some physical science in their background. What's the relationship between the charge of an electron and the charge of a proton? That's give me an idea where things are starting. It's the negative 1.6 times 10 to the negative 19th. They're just opposite charges of each other. All right, and the charge of a neutron?
Is it gonna be 0?
It will be, yes indeed.
That was a lucky guess, by the way. I have no knowledge.
I'm going to say that you do have knowledge. All right. The neutron is neutral. There's a reason they called it neutron. Now, so we've got these three components inside a nucleus. The electron was the first one found, then they found protons, and then found neutrons. About 90-some years ago, they found the neutrons for the first time. What do you know about charges? I can say the first word, and I think most of you will know what I'm talking about. But before I actually drop a hint, what do you know about charges?
They can change.
They actually can, but it depends on how you're meaning.
You got it.
Okay. If in doubt, point. All right. Opposites.
Attract.
There we go. At least two of you knew what that was. So opposite charges attract each other. So I got these protons and electrons that are really loving each other. What about like charges? If I have two electrons next to each other, what do they want to do?
It's like a battery. Not a battery, a magnet. Do they repel?
They do indeed repel. So like charges repel, opposite charges attract each other. So if I have a proton and electron, if I put a proton here and an electron here, they want to come towards each other. So let's go back to what goes into an atom. What's at the core of the atom?
Nucleus? I don't know how to say it.
Nucleus? Yes, it is the nucleus. So the nucleus, so in the core of an atom, we have a nucleus here. And this is where the protons and the neutrons hang out. The size of a nucleus is on the order of 10 to the negative 15th meters. Notice a femtometer. So the atom is 100,000 times larger than the nucleus. Obviously, the one particle I haven't mentioned yet is the electron, about where they are. The electrons are way out here. Ish. In reality, it's far more complicated than electrons. Most people give this image of this planetary model that you've got this nucleus and you've got these electrons sort of orbiting around it, and that works for a while, but at some point it really, sometimes the electrons are inside the nucleus, but that's a different story. So if I have an electron, so let's look at the planetary model. I have an electron here. The electron is actually attracted to the proton. Why does the electron not collapse in?
I don't know. It kind of seems similar to the whole, yeah, never mind. Well, it has to do with gravity, so
Not a gravitational pull this time, but there is a force there.
it kind of seems similar to the reason with the satellites don't,
And what is the reason? You're so close. Do you want to fill in the gap for Hunter, or Hunter, do you want to take it by yourself? Someone help Hunter out?
Do you mean when the electron is going through the nucleus or when it's going around?
When it's going around.
Centripetal motion or force of gravity.
Okay, in this case, the centripetal force is not force due to gravity, but there is a force holding it in. People are dancing around it, but the electron's traveling so fast it never hits. It's that constantly being pulled in.
I thought there was a definition or something.
No, I was just looking for it. It's traveling too fast to fall in. So I have this electron that's zipping around here. Now, this whole idea of the atom looking like this was relatively new. They knew about positive and negative charges. That had been figured out in Ben Franklin's days. He's the one who sort of set up the convention that he figured out current flows. He sort of imagined the electric current like a river, and that current flows downhill, and so he came up with this idea of this, he got into this potential energy thing, electric potential, which is a little bit different. And this whole idea ultimately ended up with positive charge flows. It turns out, for the most part, that's not true, but it's the exact opposite, but the convention was set in the 1700s. What he thought of as this positive charge was sort of a fluid. When they figured out the electrons, and they were trying to come up with the atom, they pictured the atom as this positive fluid kind of all around here, with these electrons sort of stuck into it. This is known as the Thomson model, and I think I'm spelling his name correctly. I can't remember if the P is there or not. The Thomson model, also known as the Plum pudding model. This is mid 1800s, mid to late 1800s, plum pudding model. And the reason why is that if you have plum pudding, apparently, with raisins in it, you get this just general mesh of this fluid-like substance, and inside there are raisins, just like electrons are like the raisins inside the plum pudding, the electrons inside this soupy positive charge. Rutherford comes along, and I mentioned this is speculation, I'm making it seem like no one had thought of this beforehand, but Rutherford's the one who gets credit for it. He took this idea and he shot these particles, known as alpha particles, at gold. And so what you would expect, if indeed it's like the plum pudding, I shoot this alpha particle, and to give you some idea of mass, the alpha particle is just actually a helium nucleus. So you've got this massive thing of, well, 4 units. Sorry, 2. Basically, alpha particle is 2 protons, 2 neutrons. Going at these tiny little things. The proton's mass, it's going off memory, that was part of my hesitation there. Proton's mass is roughly 1,000 times more than that of an electron. So imagine you've got this 2,000-pound truck coming right at you, or coming right at something that has a mass of 1 pound. What would you expect to see if that 2,000-pound truck hit this 1 pound object?
There's no more 1 pound object.
Yeah, pretty much. What's the 2,000-pound truck going to be doing? I guess it's a car, 2,000 pounds, but a 2,000-pound car, what is it going to do when it hits this 1 pound object?
Keep on going.
Yeah. So what you would expect, if the plum pudding model was right, you shoot these alpha particles at the gold foil, you would expect to occasionally see these electrons get shot out, but this, for the most part, won't deflect a whole lot. What they saw, in what I consider probably one of the most tedious experiments of all in physics, they didn't have detectors in the sense you basically are looking at flashes of light. So you get this, you have this detector that you're sitting in, that you're looking at, and so you stand right here with this detector, and you shoot an alpha particle, and you look for this flash of light
So
over here, known as scintillation.
Are you just shooting yourself with alpha particles?
Yeah, there's a certain amount of stuff that they did back then, which would be considered incredibly dangerous now. Alpha particles not the most dangerous of other radiation particles, but yeah, I wouldn't want to have that done on a regular basis. So this thing gets shot out there, and then you count. And then you move the thing over here, and you do it again. You count number here, and then here. And you would expect, if the plum pudding model is right, almost all of them are in this region right here. And then you get less and less, and it'd be ridiculous to actually see any over here. But they did. They saw some alpha particles bounce. The classic analogy that they used was like shooting a bowling ball or cannonball at tissue paper and having the cannonball bounce backwards. So they tried to figure out what on earth was it actually hitting. And so with calculations about, the number of that show up here versus here and so on, they figured out that there's this hard core nucleus that is more massive than the alpha particles. So that's how they figured out the nucleus. Now, one of the guys who was doing this experiment, one of the grad students, Rutherford had a number of grad students who all ended up winning Nobel Prizes. One of the grad students working on this project, who did not win a Nobel Prize, but probably is the most famous of his grad students, Geiger, as in Geiger counter. You can imagine you're in there counting flashes of light. It might inspire you to come up with a detector that would automatically detect this stuff, so you don't have to stand there. All right, so that's when they figured out the nucleus is there. And so that basically is the model that we're working with today. So we have this interaction of the electrons and protons. They are attracted to each other, but the electron keeps missing. The protons are so much more massive. It's like the Earth-Sun dynamic. The Earth is pulling on the sun, but the sun's not getting ripped out of where it's sitting. It's not really being pulled towards us significantly. The sun wobbles some because of us, but not of any great note. Now, what distinguishes one atom from another is the number of protons. And let's go over to the periodic table. In the upper right corner of each square, you have this number in blue. That tells you the number of protons. This number, so that is known as the atomic number. The number below, this gives you an idea of the number of neutrons. So for example, zinc has 30 protons, and it has somewhere around 35 neutrons. And the way you tell is you just subtract the two. This is known as the atomic mass, and it basically is the number of protons and neutrons. It's a little bit off of that, but that gets close enough. Now these decimal points are an indication of the fact that